everybody. We're going to do some practice problems here about solubility product, Ksp. So essentially we're looking at how um, things dissolve. So we're talking about things that typically we be think of as not soluble, but they do break apart to some extent. So some of this, if you're in class, we went over in class already. So just a reminder of how things break apart. I don't have that first one labeled as a solid, but this would be a solid and how it breaks apart if it would dissolve at all in water. I'll label these as solid as I go through here, but this would break apart into one lead and two iodides. So there'd be twice as many iodides as lead here, and this would be one silver and one iodide. I don't know why I said iodides there. These are chlorines. Sorry about that. And then this is an iodide. So the Ksp equation, just like any K equations we've used in the past, where we're going to take the products over reactants, but these are ions, and then these are showing how it dissolves in water, and then these are solids. So the solids are not included. Solids and liquids are never included. So Ksp equation is going to be Ca 2 plus in brackets, so its concentration, CO3 minus 2 in brackets. Ksp of the lead chloride, lead 2 chloride in this case, would be that, and then the Cl minus will be squared. We haven't done that for a while, so just a reminder of what we need to do with that. And then here would be this problem. So this is just like number 86 in your book, so you'll do something similar to this for your practice problems. So this is 86. The next one is the same as number 88 in your book, so you'll have very similar problems with that. Number 3 on the front of the sheet is actually just like number 90 in your book. So why don't we do number 2a real quick, and then I'll move everything down. Maybe I can do both of these real quick. So here we have mx, which will break apart into, I know that these are just both made up. Neither of these are on the periodic table. But m with some charge, really doesn't matter if it's plus 1 or minus, or plus 1 or plus 2 or plus 3, and x with, let's say, a minus 1. If these are 2 or 3, it really wouldn't matter as far as how we set this up. Ksp is going to be equal to m to the plus 1, x to the minus 1, or whatever charge that would be. It doesn't signify exactly, it doesn't show exactly which charge one is versus the other. This is a solid, so this would break apart into a certain amount, and typically with solubility it means it is x instead of x. So these would be s. So Ksp, in this case they give us the Ksp, is 1.27 times 10 to the negative 36. So we could figure out what each of these ion concentrations would be based on the Ksp. And this is the ion concentrations when it is as much as possible is dissolved. So as much as possible is dissolved, in this case a very small number, 1.13 times 10 to the negative 18th molar for both of those ions when it's dissolved as much as possible. So if we look at the next one and look at how that would break apart, I'm just going to do it right here, to 2 silvers plus a chromate ion. So things change a little bit now that we have a different situation. 0, 0, S. This is going to be 2S. And S and 2S. This is plus 2S. Sorry about that. My Ksp is going to be equal to Ag plus squared times CrO4 to negative 2. Now the Ksp for our silver chromate would be found on page 810, and that is 1.12 times 10 to the negative 12, which is equal to 2s squared times s, or 4s squared, because the 2 needs to be squared here. 4s cubed, I'm sorry. So that is 4s cubed. Divide both sides by 4 and take the cubed root. So make make sure you can do that on your calculator. If I divide both sides by 4 and take the cubed root, I would get 6.54 times 10 to the negative fifth. So that would be the solubility of the silver chromate. How much would be the maximum that could dissolve? Obviously, that's a very small amount that could dissolve in water, that many moles per liter. But when it does dissolve, silver would have twice as much of that in water than chromate. So, just so you know, if they asked, hey, what's the solubility or the ion concentrations, that's what you'd be using. You'd be doing 6.54. When it says what's the molar solubility, like this is asking, this is just the solubility of the original solid right there. If it asks what's the concentration, so that's the maximum amount of solid that can dissolve in water. If it asks what's the concentration of each ion, I would need to multiply the silver, this S by 2 to get the silver concentration, and then S would just be the chromate. So very similar type of thing here, calcium 2 plus 2 hydroxide. So we have a very similar, except for this time the hydroxide is going to be 2S, or the anion. And now if I look up the Ksp, it is 4.68 times 10 to the negative sixth. Still going to be 4s cubed. If I solve for s by dividing both sides by 4, and I jumped a step. So this 2s squared, really it's s and 2s all squared. I jumped that to that step. When I do this, I get a molar solubility of 0.0105 molar. So that's how much calcium hydroxide, that's the molarity of maximum moles per liter that could dissolve for calcium hydroxide. So obviously that's a higher number than the one previous. That's also because the Ksp is a higher number than the one previous. That is not, you cannot always compare the Ksps and say, oh, this Ksp is higher, it automatically dissolves a little bit more. You can in this case, because we're breaking into two moles of ions, or sorry, two ions here and one ion here, and the second one is breaking into 2 ions and 1 ion. But let's say that we're just breaking into 1 and 1, like we will be on the next one or on the previous one. You can only compare similar situations stoichiometry-wise, where we have 2 and 1, or 1 and 2. Those you could compare the Ksps, and then their solubilities will line up also, being this is being bigger than this, and this is bigger than this. Once you start trying to compare Ksps of different stoichiometries, or what that means, that's what they'd say in your book. What that means is we're breaking into only 2 total ions, like Na and Cl, or barium and chromate. Then you can't really compare them anymore because of what you need to do with the S's and square them and cube them and all that jazz. So you can really only compare numbers like that if you have if they're similar in what's happening, how they break apart. So then the next, number 3, again, which is number 90 in your book, is doing kind of the reverse process, because now they're giving you the solubility. I would still look at how it's going to break apart and write Ba and do an ice table. BaCrO4 it's going to break apart into barium plus chromate. 0, 0, S, S. Didn't leave myself much space. This is S, this is S. So my Ksp, which is equal to barium times chromate, I'm looking for Ksp now, but they've given me the solubility. Since this is breaking into even amounts, both S's will be the same thing. So I really could think about this and just go ahead and put that concentration. The S is going to be 1.08 times 10 to the negative fifth for both of them, and square it. That's going to give me, pick up where we left off there. So we're multiplying those two, so this would end up being squared. I had it deleted there real quick, so it ends up being that the Ksp would equal 1.17 times 10 to the negative 10th. For that one, there's just equal amounts, so this ends up being squared. So for this next one, let's see what happens here. We have AgSO3, Ag2SO3. We break into 2 silvers plus 1 sulfite. So think about this, 0s, 2s. So this is 2s, this is s. So if I'm calculating Ksp, my Ksp is actually going to equal 2s squared times s. So the concentration of Ag plus and the concentration of SO3 minus 2, which is 2s, but I need to square it because there's a 2 in front of the Ag. So in reality, it is equal to 4s cubed. If I plug in this solubility for my s, that is going to give me an answer of 1.49 times 10 to the negative 14th. So make sure you plug that in yourself. Make sure you check, make sure I'm right. So that is the Ksp in this situation by taking 4 times s cubed in this situation, where this is s. So I'm plugging this in, whoops, right there for s. Very similar situation here where we have palladium thiocyanate that is breaking apart. And we'd have 0 plus s, 0 plus 2s. So then Ksp is equal to Pd. So I'm taking a step that I didn't do last time. SCN minus squared. So the Ksp is equal to S for Pd times 2s squared. All of that ends up being 4s cubed again. Plugging in this smaller solubility for the s would give me a final answer of 4.38 times 10 to the negative 23rd. Again, since these are both breaking apart in s and 2s, I can compare these Ksps. If I was just given those two values to compare, I could do that because this is a smaller number than this, so that means that this will dissolve or dissociate more. Again, it's not much, but it will dissociate more. When we look at the solubilities, molar solubilities, how much of it can actually dissolve, the maximums to the negative 5th, negative 8th, they're both a small amount, but when we compare KSPs, they have to have the same amount that they're breaking apart to be able to compare it. All right, so on the back, we have a little change to the situation where we aren't just in water every single time. The first one is, and the answer to the first one is actually from the front, because the front, number 2A, is the same exact question. It's in pure water. This is actually number 96 in the book. So I'm going to go ahead and just jot down the answer we got for 2A on the front, what the molar solubility was, because back here it was 1.13 times 10 to the negative 18th. So how are these next two different? Well, the next two are different because they are being dissolved into a different solution which already contains one of the two ions. So like here, this contains this M ion. I know that the M is not really there. So it's M with a +2 charge because there's 2 chlorines plus 2 chloride ions. So my concentration of the M I can assume is 0.25 molar. Whoops, not 0.125. 0.25 molar. This is 0.50 molar. But I really don't care about that. What I'm more concerned about is how this MX solubility is going to be affected. So what is happening is I have an amount now. I don't have a zero amount. I have some of that already dissolved or sitting in the solution. So that's going to affect how much my new stuff will dissolve. I don't have any of this X in solution, so that'll still be 0. This will be plus S 0.25 plus S and S. Now when I set up my Ksp, which equals m plus 2 concentration times x minus 2 concentration, I am solving for the molar solubility. I know the Ksp is 1.27 times 10 to the negative 36, pretty small number. That equals a m plus 2. In this case, though, is 0.25 plus S times S, my concentrations here, or the amount that they're breaking apart. So very similar to in the past, since we're adding S to 0.25, this S is going to be negligible. The ones that I add or subtract, I'm going to assume that that S is so small that it doesn't matter. And it's going to be. So I'm going to essentially, to solve for S over here, I'm dividing both sides by 0.25. So I get 5.08 times 10 to the negative 36 molar. That's the solubility that will dissolve. That was a molar up here too. So look at the difference. When there's already some ions in there, 0.25 molar ions in there, I mean, this solubility was already quite low. Now it's even lower, way lower. Just look at the powers and how much lower it is, because there's already some of those ions in there. If we think about this one and how much it's dissolved, we're assuming that this is split into 2 sodiums plus an x minus 2. Very similar type of process where this is going to be 0.20 now. That's the only one I care about because that's affecting my dissolving of the mx. Now, let's see if I can find some room here without scrolling. If I go back to using an equation like this again, mx, m plus 2 plus x minus 2. I have a starting amount of my x now. Plus s, 0 plus s, 0.20 plus s, s. I'm going to set up just like this. It's the same substance, so I have the same Ksp. Now it's going to be s and 0.2 plus s. So really the only difference is instead of dividing both sides by 0.25, I'm going to divide both sides by 0.20. The s is going to be negligible again, so it's really a very, very similar problem. This time when I solve for s, I get 6.35 times 10 to the negative 36 molar. Very small numbers. So that's what s would equal in this case if we already had some x in solution. So it really affects the amount that will dissolve. So that was number 96 in your book, very similar to a problem that you're asked to do. And then the last one here, number 5, is actually number 100 in your book, very similar to a problem you'll be doing also. So above it was asking what happens when there's already some ions in solution. Now it's asking what if it's acidic, and really the question could also be asked what if it's basic, because we'd have to look at either one of these ions. If either one of these ions would react with hydrogen ions, it could affect how much it dissociates. So if we think about how much this dissociates, let's just do this. We can do a double arrow, whatever, but we think about how much this associates to, actually those are mercury, those are some weird ions there. But regardless, what I'm concerned about is the hydrogen ions. Since it's acidic, will those hydrogen ions join with either one of these? Well, they're positive hydrogen ions, so they're not going to join with the metal here, but they could possibly join with the bromide if this was a base. Well, we know this is a neutral ion. So since it's a neutral ion, the H plus will not bind to any of these, and it's not going to affect the solubility whatsoever. So it would not affect, there'd be no change in how much it is soluble. It would not be more soluble in that situation. Unlike this next one. Here we have magnesium and hydroxide, and this would be affected because this hydroxide will react with H plus. So what's going to happen is it's going to be a Le Chatelier's type of a situation where in the examples above we had some hydroxide or magnesium already dissolved. That would be like the examples above. Now it's like the opposite situation where as soon as we dissolve any, some of this hydroxide is disappearing. The concentration is gonna go down because it's reacting with hydrogen in the water as soon as it forms. So as soon as it breaks apart into some hydroxide, so it's actually going to increase the solubility because of that. Increase solubility. Okay, it's not the hydrogen's not going to react with magnesium ions. They're both positive, but since this is a base, obviously a strong base, but it will react with it, and it will increase the solubility. The same thing will happen on C. It will increase the solubility because calcium is a neutral ion, but CO3 2 minus is coming from a weak acid. That will also react with hydrogen. So same situation. It will increase the solubility. It will react with the hydrogen ions. This ion would. So if it's a neutral ion, it will have no effect, like this one is up here. So the one's coming from a strong acid. But any conjugate base of a weak acid or hydroxide would be affected by being in an acidic solution, because essentially those ions react, and like if hydrogen bonds to this, now there's no more, those ions aren't floating around anymore, and it allows this equilibrium to keep shifting to the right and dissolving more. Obviously it depends on how acidic it is and to what degree that would move over. The last one then is pretty similar to the first, in that this would break into silver plus double arrow it just because it's not very dissolvable, but this is silver and iodide, and this is also a neutral ion, which means it will not attract to hydrogen. It will not bond with hydrogen at all, because Hi is a strong base. The hydrogen and iodine are not attracted to each other at all. So again, no change in this situation, because the acid would not affect either one of these ions. So vice versa, if it was a base, it would have to affect or bond with one of those ions to make a change to the solubility. So you should be able to work on some of the problems that were assigned that were very similar to these.